Hello students, welcome to the session on Consolidation of Soils, Module 5, Basic Geotechnical Engineering. Today's session we will be discussing about the definition of consolidation, Terzaghi's mass spring analogy, Terzaghi's one-dimensional theory. We will also be discussing the assumptions and limitations of the theory, the basic governing differential equations, and the solutions of the one-dimensional theory. Finally, we will be discussing some important multiple choice questions relating to today's topic. Coming to definition of consolidations. As you know, the soil is composed of many particles, solid particles, and as well as it also consists of void spaces. These void spaces are generally filled with either air or water. Here, compressibility of soil occurs mainly due to the expulsion of the pore water from the voids. This process is called as consolidation. It is a time dependent phenomena. Unlike compaction, which is a sudden process. But here, consolidation occurs over a period of time and volume reduction happens due to the expulsion of water from the soil. Here, particularly, we are discussing about saturated soil. Volume reduction mainly occurs due to on account of the load acting on the soil. The load may be due to the structure or any other temporary or permanent structure which is present over the soil. In general, if we observe the figure which I have shown you here, this is a two-phase diagram of the soil which comprises of the solid and as well as the water. The void space is completely filled with water. So the figure 1 represents the state of soil before consolidation, wherein the void space is completely filled with water. Here you need to understand this is a completely saturated soil. So V1 represents the total volume of this saturated soil. Over a period of time, what happens is compressibility of soil takes place, thereby a change in volume occurs. The change in volume is represented by the delta H, and the final volume turns out to be V2. So this occurs due to the load acting on the soil, and this clearly represents how the consolidation process takes place. Moving further, we will be discussing what is called as Terzaghi's spring analogy theory. In spring analogy theory, Terzaghi assumed the container. He has considered a container which is completely filled with water, and there is a valve provided which is initially closed, and there is a in this container there is a spring which is provided, and the container is completely filled with water. As you can see, when a load is applied onto the top of the piston, while the hole is still open, when the hole is still unopened, at this stage only the water resists the applied load. What I mean to say is there is a development of what is called as excessive pore water pressure. The load acting on the container from the piston is completely taken by the water. As soon as the hole is opened, gradually water starts to drain out through the hole, and the load gets transferred to the spring. This can be explained as a process of drainage which is occurring through this excess pore water. After some time, if you observe, there will be no drainage of water, but the load completely will be taken over by the spring alone. This is on account of the full dissipation of excessive pore water pressure, which uh, terminates the process of consolidation. So, how the load transfer generally takes place in the spring analogy theory can be explained with the help of this figure uh, on the top, which clearly shows a container with a piston over the top, and the piston is also provided with a valve opening, a tube opening, which is controlled with the help of a valve. Initially the load will be, if you can observe the figure A, the load will be taken Pw plus Ps is equal to P, where P represents the load, Pw represents the load carried by the water, Ps represents the load carried by the spring. For what happens here is, as you can see, initially the load will be taken by the water at time t is equal to 0. Therefore, the load carried by the spring Ps will be equal to 0, and the total load carried by the water will be equal to 1. As you know that Pw plus Ps is equal to 1 if you consider 1 kilonewton of force which is acted upon over the piston. Now, if you observe, if the valve is opened gradually, there is a change of, or what you can call as a shift of load from the water to the spring. Now this can be explained as delta P is equal to the total load 1 minus the delta P, which is equal to 1. What is actually happening here is, there is the dissipation of excess pore water pressure, and the load taken by the water is getting transferred to the spring. Finally, when the valve is completely opened, what happens here is the load completely will be taken up by the spring. So the total load taken by the spring will be equal to 1, and the load taken by the water will be equal to 0. If you observe the graph which I shown to the right side of you, that represents the load sharing between the spring and the water. Initially, if you can observe, at time t is equal to 0, the load will be completely taken by the water, and that is equal to 1, and that is equal to 1. As the time progresses, gradually the load will be taken by the spring, and at time t is equal to tf, the load completely will be taken up by the spring, and the load will be equal to ps is equal to p, where p represents the total load. Next, we'll be discussing what is called as Terzaghi's one-dimensional consolidation theory. This is a very important theory which is proposed by Terzaghi, um, and the assumptions of this theory are like this. Terzaghi assumed the soil to be homogeneous and fully saturated. He also assumed the soil particles and water are incompressible. That means it cannot be compressed. They are incompressible. Darcy's law for the velocity of flow through the soil is perfectly valid. Coefficient of permeability K is constant during the process. It means to say that the water flows freely, and the coefficient of permeability also will be taken to be constant. Soil is laterally confined so that the compression is one dimensional. This is a very important assumption because yeah, Terzaghi assumes the compression to take place in one direction. So uh, it is not being assumed in to take place in two dimensions. It is a one dimensional compression which is taking place. That is one of the important assumptions. Excess pore water drains out in the vertical direction only. This is not practically possible in a field, but for these assumptions and for this theory, this is assumed in this way. Linear relationship between effective pressure and void ratio exists and are constant at every stage of consolidation. The time log of consolidation is entirely due to low permeability of soil, and thus secondary consolidation is also disregarded. Coming to this theory, if you can observe the figure, in this figure, there is a section of clay layer which is chosen, and the top and the bottom of this layer is consists of sand particles. Okay, as explained in the spring analogy model, initially the whole of the pressure is taken up by the water, and the excess pore water pressure develops. In this figure, if you can clearly see that the hydrostatic pressure diagram on the right hand side, it is assumed that the various points along the thickness of the clay layer are connected by flexible tubes, and at time t is equal to 0, just after the application of the load, the excess hydrostatic pressure is equal to delta sigma by gamma w throughout the clay layer. This is represented by the horizontal line. So the excess hydrostatic pressure is independent of the position of the water table. For example, the water table is assumed at the level of the surface of the clay layer. Okay. So now if we can observe at the instant of loading, that is at time t is equal to 0, the excess pore water pressure will increase uniformly by ui over the thickness h of the layer. As you can see here in the please observe the figure which I have shown you at the top. The layer is divided into two parts, that is h by 2 and h by 2, where h represents the thickness of the overall layer. After a time t has elapsed, what happens? Because of the drainage into the sand layers above and below, the distribution of excess pore water will have changed the shape of the pressure distribution diagram, which is represented by a curve in the figure B. Please observe the shaded portion. See, if there are two drainage surfaces, one as shown in the figure A, that is one at the top and another at the bottom of the consolidation layer, it is called as double drainage layer, and H, capital H, will be equal to half of the clay layer, that is H is equal to H by 2. I repeat again, one at the top and another at the bottom. If there are two drainage surfaces, then the thickness of the clay layer will be equal to H is equal to H by 2. But if there is only one drainage surface, it is called as single drainage layer, and H will be equal to capital H, which is equal to the thickness of the clay layer. Finally, when we solve this equation, we arrive at the Terzaghi's one-dimensional consolidation equation. It is represented by the equation shown you in the slide. This clearly explains the variation of pressure with respect to time and with respect to the depth. This is a basic differential equation of one-dimensional consolidation. It gives the distribution of hydrostatic excess pressure, that is U bar, with respect to the depth z, and the time t. In the Terzaghi solution, there are three important factors which he discusses. One is A, that is drainage path, that is capital H. Another is time factor, TV, and most importantly, he discusses about the coefficient of consolidation, that is represented as CV. Here, the time factor is TV is given by the equation TV is equal to CV into T divided by capital H square, where TV represents the time factor. T is time, small t is time in seconds. Capital H represents the thickness of the permeable layer. Okay, and CV can be obtained, that is the coefficient of permeability can be obtained by the equation CV is equal to K divided by MV into gamma W, where MV represents the coefficient of volume change and can be represented by centimeter square per gram or meter square per kilonewton. CV can also be written in the form CV is equal to K into 1 plus E divided by AV into gamma W. This equation represents the coefficient of permeability, coefficient of consolidation in terms of coefficient of permeability and void ratio. So here K represents the coefficient of permeability, centimeter square per second, and E represents the void ratio, AV represents the coefficient of compressibility. Next, coming to the limitations of the consolidation theory proposed by Terzaghi. This is a one-dimensional, as I told you. The deviation of one-dimensional equation occurs and the coefficient of volume compressibility progresses through the void spaces and decreases, and this results in the decrease of permeability, and therefore the permeability value is not constant. The coefficient of volume compressibility also changes with change in the stress levels. Therefore, the coefficient of consolidation is not constant. Another important limitations in this theory is that the flow is assumed to be one dimensional, but in reality, as I told you, the flow is three-dimensional. So this is one of the important limitations. The applications of external load is assumed to produce excess pore water pressure over the entire soil layer, but in some cases the excess water pressure does not develop over the clay stratum. This is particularly due to the application of the external load, how the load acts on the soil stratum. The load distribution will not be uniform. So coming to the final part of the presentation, here I'm discussing some of the important multiple choice questions. The consolidation of soil involves A. Settlement of soil, gradual drainage and compression, compression of air in the pore spaces present in the voids, or none of the above. The answer is gradual drainage and compression of water through the voids. Second important question, that is rate of consolidation. What is rate of consolidation? Is it increase with it? Does it increase with a decrease in temperature, or does it increases with increase in temperature? Is it dependent on temperature, or is it unaffected by the permeability of the soil? The answer to this question is B. The rate of consolidation increases with increase in temperature. The unit of consolidation, centimeter square per gram, centimeter square per second, gram centimeter square per second, gram second per second. The answer is centimeter square per second. The coefficient of the volume of compressibility in soil is it proportional to the void ratio? Decreases with increase in the void ratio, is inversely proportional to the void ratio, is inversely proportional to the square of the void ratio. The answer is B. The coefficient of volume compressibility in a soil is inversely is it decreases with increase in the void ratio. The compression index of soil decreases with increase in liquid limit, decreased with plastic limit, increases with increase in liquid limit, or is it totally unrelated with the plastic limit? The answer is increases with increase in liquid limit. The compression index increases with increase in liquid limit. Next question is, the ultimate settlement of soil is directly proportional to the depth of soil strata, inversely proportional to the depth of the compressible soil strata, directly proportional to the depth of the compressible soil strata, or unrelated with the depth of the soil. The solution is C. The ultimate settlement of soil is directly proportional to the depth of the compressible soil strata. Coming to the last question. Within the consolidation of a process, a gradual increase in neutral pressure, a gradual decrease in neutral pressure, or is it due to both neutral pressure and effective pressure, or both neutral pressure and effective pressure increases? The solution to this question is B. There is a gradual decrease in the neutral pressure. So, coming to the end of the presentation, these are some of the references. Thank you.